We talked about the Wronskian as a tool for us to determine whether functions are linearly independent. And as long as we have the same number of functions that are linearly independent as the order of our differential equation, we can put it together as a linear combination for the general solution. Yeah?
The Wronskian is the one where it equals to 0, right?
If it's equal to 0, it's dependent. And if it's not equal to 0, it's linearly independent. So if you have a set of functions that are linearly independent and they satisfy the differential equation, we call that a fundamental solution to the differential equation. And if you have a fundamental solution to your differential equation, a set of functions, then the linear combination of those functions will be your general solution to the differential equation. So for higher order differential equations, we should expect as many of these arbitrary constants as the degree or as the order of the differential equation. For the first order, we came up with the 1 plus c somewhere along the line. For second order, we should have 2 c's, and they will end up being coefficients of some functions, of some fundamental functions. All right, I think that's where we left off last time, so let's continue on building more theory behind these higher order differential equations. So remember that a homogeneous differential equation is that differential equation set equal to 0. So if you have a differential equation that's not set equal to 0, where g of x is not exactly 0, then you have what's called a non-homogeneous differential equation. So the idea behind this is that if you could find a function, so these functions that we were talking about earlier is for the homogeneous differential equation. Maybe I should put this on another page. Let me do that. So for non-homogeneous differential equations, one of our main goals is to find what's called a particular solution to that differential equation. And that particular solution would be a solution that would satisfy this differential equation. Now notice some of your homework problems is asking you to find the solution to the differential equation by inspection, which means you basically guess. You guess your solution. And it's okay to guess sometimes. It builds intuition if you can guess the solution to your differential equation. And we'll see that finding this particular solution might not be so easy, but we'll build on trying to find these solutions as we continue studying these differential equations. So, provided that we can find that particular solution, it turns out that adding that particular solution to the general solution of the homogeneous differential equation. Now remember, this is a solution for the non-homogeneous differential equation. But here is a general solution to the homogeneous differential equation. Then what we could say here now is that we have the complete full solution. This is a general solution to your non-homogeneous differential equation. So the idea is, if you have a non-homogeneous differential equation, the idea is to first find the solution to the homogeneous differential equation, and then find a particular solution, and then just add them together, and then you will have your general solution. So remember, this is general solution, but this is a general solution just for the homogeneous differential equation. This is a particular solution to the non-homogeneous differential equation. And by putting them together, you get the general solution for the non-homogeneous differential equation. Okay? That's all confusing? That's a little confusing. Okay, so all this is based on what's called the superposition principle, and so that's stated in the book. And I think I just copied this directly from the book. I didn't even bother typing it up. So this says that if you have several particular solutions, then you can just basically string up your particular solutions by adding them. You probably should be doing an actual example. Actual solving for this stuff doesn't come up until later on. Let's see. I don't know if I can come up with an example off the top of my head. I don't know. Maybe we just look at the book and see what kinds of problems they give you. So independent so let's take a look at these are homogeneous equations. Let's see. This is probably an example I should have showed earlier. I think they're missing an infinity here. So they're saying that these are all solutions. And let's just say by inspection, I could pretend to do the Wronskian, but by inspection this looks like it's going to be that they're all linearly independent. The 1 and the x and the cosine x and the sine x are all linearly independent functions from each other. But you can check it out or verify that by using the Wronskian. But I want to see if this actually works. I want to know if this satisfies a differential equation. So y1 is equal to 1. I need 4 derivatives for that. Yeah, so after the first derivative, you get 0 already, so you'll eventually, in 4 derivatives, get 0 again. So it looks like the fourth derivative, 0, plus the second derivative, which is also equal to 0, is equal to 0. So y is equal to 1 is a solution to this differential equation. All right, let's check y is equal to x. So the first derivative is 1, the second derivative is 0, and then that gives us to the fourth derivative, which is also equal to 0. So that works also. Maybe I should have done this example on the first slide that I had, because that's what this example is about. This is a homogeneous differential equation, right? So I'm going to move the slides around later. Let's take a look at our third solution. So the first derivative is negative sine. The second derivative is negative cosine. The third derivative is positive sine. And the fourth derivative is positive cosine. So I want the fourth derivative, cosine x, plus the second derivative, negative cosine x. So yes, this is in fact equal to 0. So I know that works. And can I just convince you that this is the same thing? Sine x also works. All right, now that we know all that, the next thing they want us to do is form your general solution. So your general solution is going to be basically a linear combination of all these functions. So it's c1 times 1 plus c2 times x plus c3 times cosine x plus c4 times sine x. And that's your general solution for the homogeneous differential equation. And before I forget, I'm going to move this page already. So this is a statement that says you string up your homogeneous differential equations, solutions for that, and then this is how it would look like. Okay? Now we still don't know how to find these actual values, and it looks like we're going to have to wait till next week to do that. But for now, this is, we're just still building on the theory. All right, so now non-homogeneous business, it starts to talk about a particular solution and the superposition principle. So let's see if we can come up with an example here in the book. For non-homogeneous equations, verify that the given 2-parameter family of functions is a general solution. I don't know if I want. No, let's do this one. It's probably going to be similar to the homework that you're going to get. So we have this business over here. They're giving us a general solution already. If you look at the general solution, let's break it down to different parts. This part over here is a general solution to the homogeneous differential equation. And this function over here, so the general solution to the homogeneous differential equation has C1 and C2, has those arbitrary constants. And this is a second order differential equation, double prime, so we should expect two arbitrary constants. The other function that's sitting on the outside is what they call a particular solution. And it's a particular solution to the non-homogeneous differential equation. This is the non-homogeneous differential equation. So if we take the general solution and plug it into this DE, we're not going to get something that's correct here. Right? Why? If I take this general solution, just these two functions over here, if I plug this into to this differential equation, what's going to happen? You guys know what I'm talking about? No? You understand my question? Should I rephrase my question, or should you just answer my question? So, if I were to focus just on the general solution part, general solution to the homogeneous differential equation, it's a solution to the homogeneous differential equation. So if I try to find y prime and y double prime of that and plug it into this differential equation, I'm not going to get a true statement, because I'm only going to get this left-hand side to equal to 0, because it works for the homogeneous differential equation, right? Let's actually see that. So this is 2c1 e to the 2x. I'm going to call this y sub g, because it's not the whole y. It's just y sub g, g for general, plus 5c2 e to the 5x. And then take the derivative one more time to get the second derivative, because that's what I need in my differential equation. I'm going to get 4c2 e to the 2x, and then 25c1, 25c2 e to the 5x. Right? No, we'll need to include the particular solution if we want it to satisfy that. So I just want to show you that this isn't going to work. So if I plug that into the differential equation, I have y double prime minus 7y prime plus 10y. And that is supposed to equal to 24 e to the x. What's going to happen? Well, I got 4c1 e to the 2x plus 25 c2 e to the 5x minus 7 times 2 c2 e to the 2x plus 5. Oh, this is c1. This is c2 e to the 5x plus 10. And then the original y, the y general, is c1 e to the 2x plus c2 e to the 5x. And I'm not counting this part yet, because we're doing something where this is for illustration purposes. This isn't actually solving this problem. And this is supposed to be equal to 24 e to the x. So if we work things out, we combine all the e to the 2x's. This is 4 minus 14 plus 10. That's the c1 e to the 2x. And then I'll combine the ones with the 5x's. That's 25. 7 times 5 is 35 with a minus. And then 10 times itself is just 10. And we see that this all amounts to 0, which is what we would have expected, because this is a solution to the homogeneous differential equation. But it's not the solution to the non-homogeneous differential equation. Okay? So that's a little side note that's important to look at. Now, before we actually answer the question, let's take a look at this particular solution, yp, and that should satisfy the differential equation. So let's take yp, take the derivative once, take the derivative again, and then put it into this differential equation to check. So y double prime, that's 6 e to the x, minus 7. Y prime, that's 6 e to the x again, plus 10. Y, that's 6 e to the x. And we'll see if this is equal to 24. So we basically have 6 minus 7. Oh, no, minus 6 minus, oh, I hate this. 6 times 7 is 42. And then 60. And this, I hope, is 24. Is it? What? 24. Yeah, good. So this does work. So this is a particular solution to the differential equation. Yeah?
We always have to check
No. No. Well, this particular problem isn't asking you to do either of these. I'm just doing this for fun. What this problem is actually asking you is this whole thing put together to check it like that. And so that's about what we're going to do next. All right, now let's really answer the question. To answer this question, we want to check if this thing satisfies that differential equation. So for this, we need y prime and y double prime. Basically, I already kind of did them already, but let's do it again. C1 e to the 2x plus 5 c2 e to the 5x plus 6 e to the x. And then we'll put it into this differential equation. So we have the y prime, or y double prime, minus 7 times y prime plus 10 times y is hopefully equal to 24 e to the x. So let's put all those values in that we found. We found y double prime to be 4c1 e to the 2x plus, oops, I'm writing too big, 25c2 e to the 5x plus 6 e to the x. That's y double prime. Negative 7 times y prime, that's 2c1 e to the 2x plus 5c2 e to the 5x plus 6 e to the x. And then the original y, c1 e to the 2x plus c2 e to the 5x plus 6 e to the x. And if you work all this out, you could just trust me that this is going to be equal to 24 e to the x. We actually did the work already. We did it separately. You know, if we combine the homogeneous part, we're going to get 0, plus we combine the particular solution part, we're going to get 24. So we did the work already. But that's essentially what you're trying to do here. So this, in fact, is a solution to our, now we actually have the general solution to the particular solution, to the general solution to the non-homogeneous differential equation. Okay, look good? All right, let's see if there's any more interesting problems that would invoke some of those theory things that we're looking at. Let's take a look at number 35 to see what they mean by this superposition principle. And this is kind of like how the superposition principle works. So we want to verify a couple of things here in the beginning. We want to verify that 3e to the 2x is a particular solution to this first differential equation, and we want to verify that x squared plus 3x is a particular solution to the second differential equation. So let's try to do that up on top really small here. So y sub p1 is equal to 3e to the 2x. We want the first and second derivatives of that. So y sub p1 prime is equal to 6e to the 2x, and y sub p1 double prime is equal to 12e to the 2x. Right? Now let's plug those values in here to see if we're going to get what we're supposed to get. I have a 12e to the 2x minus 6 times y prime, which is 6e to the 2x, plus 5 times y, which is 3e to the 2x. And we want to know if this is equal to negative 9e to the 2x. So I think all we have to do is try to see what these coefficients turn out to be. So I have a 12 minus 6 times 6 is 36, plus 5 times 3 is 15. And does that amount to negative 9? Yeah. So this first one is verified. Let's do the next one where we're looking at the next solution, x squared plus 3x. We need the first derivative, 2x plus 3, and the second derivative, which is 2. And then let's plug it into the second differential equation. So this looks like it's going to start off with a 2 minus 6 times the first derivative. It looks like it's a 2x plus 3 plus 5 times this original function, which is x squared plus 3x. And hopefully this will be equal to this thing. Let's see. I got a 2 minus 12x minus 18 plus 5x squared plus 15x. Five x squared positive 3x negative. So that checks out. Okay, so that's the first part. Is that cool? Now let's take a look at this differential equation over here for part B. Notice that, you know, the left-hand side is still the same, and that's important to note because all this kind of stems around to the idea that it's a homogeneous part is the same. Yeah.
So from my understanding, like, if I were to solve that problem, I would use YP1 on both of them. Because you just did the YP2 on the second equation.
Yeah, so that's the first part that they're saying here is that verify that YP1 is a solution for this one and YP2 is a solution for this one. Yeah.
So it wouldn't.
That's when they say respectively.
Okay.
But one is not going to be a solution for the other, right? So those two are separate. However, I don't know if that's a however transition. So I need another transition. Moreover? No. Transition, whatever. Whatever. We were looking at this superposition principle idea that says, all these are kind of confusing looking, right? So let's see how this thing translates to the problem that we're doing right now. What we want to do is we want to focus on this differential equation right now. We actually found a solution, a particular solution to the non-homogeneous differential equation where the right-hand side is equal to negative 9 times e to the 2x. And they also gave us the solution to the differential equation, a non-homogeneous differential equation where the right-hand side is equal to 5x squared plus 3x minus 16. So it's not a coincidence in this particular scenario that we actually have the right-hand sides to the differential equations that we were verifying. So a particular solution for this differential equation would be a particular solution that solves a non-homogeneous differential equation where you have the first thing added to a particular solution where you have the second thing. You see how that goes? So in other words, a particular solution by the superposition principle, superposition principle. Wait, is it called the principle? Yeah, superposition principle. Principle. Yp for this particular differential equation is going to be these two things added together. No constants or no arbitrary constants, but just those two things added together. So 3e to the 2x plus x squared plus 3x. That is your particular solution to this slightly more complicated differential equation. So the idea is that if you can, I don't know if I want to do this, but you know, we could take the first and second derivatives and plug it in here to make sure it'll work. But if you just trust me. So take the first and second derivatives of this y sub p over here that we just got, and then plug it in into this new differential equation, y double prime minus 6y prime plus 5y equals 5x squared plus 3x minus 16 plus 9 e to the x squared, e to the 2x. And if you plug it into there, you should get the correct answer, or you should get a verified tautology, a true statement. Tautology. Oh. It works? All right, it works. Okay, so I won't do that. Leave it up to the reader. You do it. But let's take a look at this last part of this question. So we've got all these things verified, and it's all done. This one we didn't quite do, but you know, you assume. But now let's look at this right-hand side, this non-homogeneous right-hand side. This looks weird because it doesn't look like anything that we have here. Although it kind of looks close to that, right? So what I want you to do is think about breaking this up into two different functions again. Compare it to these two functions that we have, and see how you can adjust your y sub p1 and your y sub p2 so that they might satisfy this differential equation. Make 30 seconds to think about that and see if you guys have any suggestions, and then I'll put it in there and I'll try it out. Or I'll have Wolfram Alpha try it out. If we multiply this one by -2, is this what you mean by the top one? So 2, -2 times 3e to the 2x, That might do it. Okay, how about this one? What do you do with that one? While you guys are thinking, I'll boot up Mathematica, so I'll be ready. Say it again? The other one also by -2? We'll see if that works out. All right. Let's get some Mathematica going here. So I'll start off by defining my two functions, and I'll define it the way Mathematica likes it defined. So it's -2 times 3 e raised to the 2x power. Let me put a times here just to make it clearer. And the second function is -2 times x squared plus 3x. So I want to find out what y particular So let's just compute the right-hand side to see if it looks like it's going to work. So y, it's not going to work? Or did I type something wrong? Okay, so let's see. It might not work. So the double prime minus 6 times y prime plus 5 times y. Okay, let's see how this is going to work out. Oh, let's simplify it. So we got, if I'm going by the order of terms here, we got -10 x squared minus 6x. 2 times 16 is plus 32. And then I get plus 18. So the first one should have been divided by 9? Or should we divide by 9? All right, let's see what happens. So I got the -10x squared minus 6x plus 32. Oh, then I have a negative sign. So what? Let's throw a negative in front of that. Let's try it again. So a -10x squared minus 6x plus 32. Now we got the plus e to the 2x. Wow, that was a lot easier than having to compute it ourselves. So you could throw this in our notes to see and show that we verified it. But it looks like should have been a negative 1/9. So you guys got this to be negative 2. How did you decide to get a negative 2 here? For those people that said negative 2. Somebody said negative 2 and I wrote it down. So maybe that one or maybe two other people understood why. So now I want to know why for the other people that didn't understand why. All right, so that's where the negative 2 comes from, multiplied here. So is that the same thing that's going to go work over here? So you have minus 1/9 multiplied by negative 9e to the 2x. Right? Those are those two functions again. If you want to get back to those two functions. If you know the solution to something, and then you have another differential equation that looks almost similar, except maybe you're off by a factor or a constant, then that's how you can find another particular solution, by changing the factor or constant by something. Okay, so we understand where the negative 2 came from. It wasn't just a plug and check, although that's what we did. We checked it, and then we see it worked. We see that it didn't work, and so we adjusted it. But really, it wasn't just a guess to see where negative 2 and negative 1/9 came from. It actually does come from this. Right? Okay. So that actually, this Mathematica demonstration here, we could have taken the same differential equation and just, if we did it one by one, no, never mind. I was thinking about something else. All right, let's move on. So you have the idea behind the superposition principle. It's just adding more solutions to it. If your right-hand side of your non-homogeneous differential equation has a mix of different types of functions, here's a polynomial and an exponential function. What you need to do is you need to find the solution, the particular solution to the non-homogeneous differential equation with just the exponential function first, and then to just the polynomial. And once you found those two, then you can put it together and add it by the superposition principle. And that's the nice thing about the superposition principle, is just you collect it piece by piece, and then you just add them up all together. Okay? All right. All right, here's a summary. Do we need to take a look at the summary? Still haven't done any problems with this yet, but here's a summary. The summary is to find the solution to the homogeneous differential equation, and the solution will have your arbitrary constants. And then the next part is that if you have a non-homogeneous differential equation, is to find the particular solution for that homogeneous differential equation, and then put them together by just adding them. So I'll put this in our notes, but I won't talk much about it. And yeah, so what I'll probably do is I'll probably refer back to these notes when we actually start solving for these differential equations a few sections from now. Okay. Sometimes it's useful for us to, if we found one solution to a differential equation, we can use that to help us find another solution to the differential equation. And we can do this by substituting. And what happens when we do our substitution is that we hope to reduce the order into something that we can handle. Basically, we know how to do first-order differential equations, right? So the idea is that if we have a second-order differential equation and we have one solution, we can use that to to find the second solution to our differential equation. So here's the statement here. Suppose y1 is a solution, then y, your new variable or your old variable, is equal to u. Y1 is also a solution. And then after the substitution, you can try to solve for u, making another substitution when w equals to u prime. What? What's w? Well, let's do an example. We'll see what this thing says. If we could figure out what this means. The key here is that we need a differential equation that already has a solution. It has one solution. And so here's an example. We have y double prime minus 4y prime plus 4y is equal to 0. So we have a second order homogeneous differential equation. And fortunately, they give us a solution here. One of the solutions is e to the 2x. So let's see. What do they tell us to do? They tell us to set y equals u of x times e to the 2x. And they're saying that this is also a solution to the differential equation. So that means if we put that in here, we should still get a true statement, right? So let's take the first derivative. Oh boy, product rule stuff. Derivative of the first plus the second times the second plus the first times the derivative of the second. So I made a little bit of room here for the constant. So that's the first derivative. I have to go find the second derivative. Y double prime is equal to, I'll need to do two product rules now. It's all right. Derivative of the first, that's u double prime, times the second, e to the 2x, plus the first, that's u prime, times the derivative of the second, that's e to the 2x times 2. I'll put the 2 over here this time. All right, that's the product rule for the first one. I need the product rule for the second one. Derivative of the first times the second. I'm just going to put 2u as like one term or one factor. Derivative of the first times the second plus the first That's 2 u of x times the derivative of second e to the 2x times 2. Now I think we could simplify this a little bit. I got a u prime double prime times e to the 2x. I got a u prime here and a u prime there. They have 2's with them, so 2 plus 2 is 4. And then my last term is another 2 plus 2, or 2 times 2, 4 u of x. So if this is a solution, if I plug this into y double prime and I plug the y prime into the y prime and in the original equation y, I should get a true statement for my differential equation. So let's plug that in to here. So I'll start off with this long string of stuff. So that's y double prime minus, I need to write a little bit lower here, 4 times the y prime is here, that's the y prime, plus 4 times the original u of x e to the 2x. Whew. All right, let's see if we can take this apart a little bit. We have just one u double prime. Okay, how many u primes do we have? We have 2 u primes. There's positive 4 and negative 4. So that's gone, right? And we have 4 minus 8 plus 4. 4 minus 0. Wow. That was okay. So now what we have here is essentially u So what we would normally do is make the substitution to reduce the order, but we don't actually have to do that because this is actually a separable differential equation already. In fact, I can divide out by e to the 2x since it's never going to be equal to 0. You can divide by that. U double prime of x is equal to 0. So separable differential equation, you just take the antiderivative a couple of times to get u, right? So u prime of x, antiderivative of 0 is c, or 1, times c. You want to think about it as a constant. But you know how we took, when we found the integrating factor, when we integrated, we just said, oh, let's ignore the constant there. So we're going to ignore the constant here too. That's just 1. And then integrate again. What's the integral of 1? It's just x. So is that my other solution? So according to this, the solution that I'm looking for is u of x times the first solution. So u of x, we found u of x to equal to x, right? That's not us. U of x is equal to x, so your new solution is equal to u of x times y1 of x, which y1 of x is equal to e to the 2x. So now you've found another solution to your differential equation. So is this really a solution to the differential equation? Well, we can check. I don't want to, but we could check by taking the first and second derivatives and putting it back into the original equation. So let's check. I don't want to because it's a product rule again. Let's see, 2e to the 2x plus 4x e to the 2x. So let's put that into the differential equation where it's y double prime what is it? Minus 4y prime plus 4y and you'll see that it's almost the same work as we did earlier, except instead of x, we actually, instead of u, we actually have an x in there. So you're going to get the same result. Let's see. They all have e to the x's. The only difference is that some are constants, some have an x in front of them. So let's count out all those e to the x, e to the 2x, e to the 2x. So 4 minus 4 e to the 2x, that's 0 e to the 2x. We have 4x e to the 4x, or 4x e to the 2x minus 8x e to the 2x plus 4. So it does work, and we have found another solution. And just to verify, this is actually, using the Wronskian, this is actually linearly independent from the other first equation that we found. So now we can say that our general solution is going to be the first one times C1 plus the second one times C2. And the second solution that we found was the same as the first, except it's multiplied by x. Okay? All right, so if we have one solution and we know that we need two solutions because it's a second order differential equation, now we know how to find that second solution. We find that second solution by doing this business. Okay, that was a lot of business. Should we do another one? Or we could be done. Yeah, for a third order differential equation, except it's going to be a little bit more challenging because you need two of them. I kind of want to think about it as like solving a polynomial. If you have like a third degree polynomial, you could do long division to factor out one factor, and then now you have a second degree polynomial, so that's quadratic. You factor that out, and then you get just a linear polynomial, so it kind of reduces the order that way. Except instead of using division like in algebra, this is using just some calculus with derivatives. So it's the same idea. All right. So this is generally what 4.2 is about. We'll use 4.2 when we start building up our solutions, and we will actually solve things from scratch now, starting in the next class with 4.3. So 4.3, we're going to get introduced to a way to solve these homogeneous differential equations. And then 4.4, we'll take a look at non-homogeneous parts. All right, I think we can be done today. Your exams are, I don't know where they are.